let's start with the first problem. Given a binary tree and it has n leaf nodes, and we had to find out number of degrees, number of nodes with degree 2. This is what we need to find out. So we can just simply draw a tree, something like this. Now we know that it has n leaf nodes, right? So here we have 3 leaf nodes. So n is equal to 3. And number of nodes of degree 2. That's what we had to find out. And here we know number of nodes with degree 2 is this one and this one, right? So number of nodes with degree 2 is 2. Okay. So just by drawing a simple tree itself, we know that if n is equal to 3, then the answer should be 2. So from that, we know that the answer C is wrong, D is wrong, right? If this is true, it should applicable to any tree, right? So this is also wrong. So the answer should be n minus 1. So another way is actually just that is a standard procedure. Usually in exam hall, right, we have to solve it fast. Okay, I will also tell you the standard procedure how to solve this. So that is actually we have discussed anyway. I will tell you again. So we will actually create 2 equations. One is, let's assume we have n0 is the number of leaf nodes, n1 is the number of nodes with degree 1, and n2 is the number of nodes with degree 2, right? So we know that the total, let's assume we have total x nodes. I'm using x because we are already having n here, so it's better to use some other variables. So I'm is equal to number of nodes with degree 0 plus number of nodes with degree 1 plus number of nodes with degree 2. So this is equation number 1. Okay, and we also know that in a tree, if you have x nodes, we will have x minus 1 edges, right? So I know we'll have x minus 1 edges. And I also know that the degree 0. So if you see here degree 0, right? This is degree 0. Or I can add one more. Okay. So these 3 are actually having degree 0. So degree 0 nodes are not contributing any edges. But degree 1, if you see, this is degree 1, right? Degree 1 edge will contribute one edge, right? Degree 1 node will contribute 1 edge. So I know 1 into n1. So the total number of edges will be 1 into n1 plus a node with degree 2 will contribute 2 edges. So I know 2 into n2 should be equal to number of edges. So from this I know x is equal to n1 plus 2n2 plus 1, right? This is equation number 2. Now I want to express, I want to find out number of nodes with degree 2. So I need to get the answer for n2, right? So what I'm going to do is I can subtract 2 minus 1. What I will get, x minus x will be 0. n1 minus n1 will be 0. 2n2 minus n2 will be n2. Right? Here I will have 1. And here I will have minus n0. Okay? Right? So n0 is equal to n2 plus 1. Or n2 is equal to n0 minus 1. So I want to find out number of nodes with degree 2, that is n2, is equal to n0. n0 is number of nodes with degree 0, that is given as n. So it will be n minus 1. So the answer should be n minus 1. Is this clear to everyone? Okay. So can I proceed to the next question? Now your time starts now. As you mentioned, most of you mentioned, the answer should be B. So we are getting, it's said that the following nodes are inserted into a binary search tree in the following order. So one by one it is inserted. So the first node is 50, right? First node is 50. Now we know that all the nodes less than 50 will go to the left side and all the nodes greater than 50 will go to the right side, right? So I had to find out number of nodes in the left subtree and right subtree. So basically I have to see how many nodes here are less than 50. So 15 is less than 50, right? Then I have 5, 20, then I have 3, 8, 37, and 24, right? So I know that there are 7 nodes that is less than 50. And in the answer, we have only one choice with starting with 7. So the answer should be B. Next question. This is a gate 1996 question. So at that time we may have multipliers which are correct. Okay. So now listen here. So the question is, everyone listen here. Okay. A binary search tree is used to locate the number 43. Which of the following probe sequence are possible and which are not? This is the question. So that means we have a binary search tree and we are searching for 43, right? So let's take the choice A. So it says the first element is 61. So definitely it should be a root because here we are starting. And since we are searching 43, we will be going left of this binary search tree. Then we are seeing 52 there, right? So 52, that is correct. Since we are going search 43, we will be going left. And we are seeing 14, that is correct. So we are searching for 43, so we should go right. So 14, then we are seeing 17, that is also right because 17 is greater than 14. Then we will go right and we are seeing 40, right? Then we'll go again 43, right? We are going right and we are seeing 43. So this is actually a valid probe sequence. So A is a valid probe sequence. Now let's see what is choice B. B means we are starting from 2 and we are searching for 43, right? So root is 2, then definitely we'll go right and we are seeing 3, that's fine. Then we are searching for 43, we'll go right? So we are seeing 50, that is perfectly fine. Then we'll go left. So we are expecting a number less than 50, right? So if you see it is 40, that is also fine. Then 43, that means we'll go right. We are expecting a number greater than 40, that is 60 here. But you see what happened here is, if this is a tree, we have a node 50 here. So all the elements left side of 50 actually should have a value less than or equal to 50, right? But we have a value 60 here. That means this is not a valid probe sequence. Right? Let's take the choice C. You are starting with 10, then you are going right 65, then you are going left, that is 31, then you are going right, that is 48, then you are going left, that is 37, then you are going right, that is 43. Is there any problem with this choice? No, right? Let's take the choice D. So it starts with 81. Then we are going left, that is 61. Perfectly fine. Then again we'll be going left, that is 52. Then again we will be going left, that is 14. Then we'll be going right, that is 41. Right? Then we are getting 43. This is also right, no issues. Right? Then the last choice, that is E. You are starting with 17, then we are going right, that is 77. Then we are going left, that is 27. Then we are going right, that is 66. Then we are going left, that is 18. Here there is a problem because in right side of 27, all the nodes should have value greater than 27, but we have 18, right? That is less than 27. Choice E is wrong. Now everyone listen here, okay? So the question is, we have to find out which of the following sequence is a valid pre-order traversal, right? So basically, if it is a valid pre-order traversal, then we should be able to construct a binary search tree with that pre-order traversal, right? That is the meaning. So we know, given a pre-order traversal, how to construct a binary search tree. That using stack, we have learned that, right? So we can use that method, but actually we don't need a stack because we know where to go. Stack is actually to remember where to put the left child or right child, because we can see the entire thing clearly. We can actually directly solve this. Okay. For example, you take the choice A. So it's a pre-order. So that means 5 should be the route. And I know all the values should be less than 5 should go left. So this is a pre-order. So definitely the next value should be 3. Then it is printing 1. So 1 should be here. That is fine. Up to 531, it is correct. 531 is correct. 531 is correct. Now I had to put 2. So 2 should be actually right side of 1. Okay. 2 should be right side of 1 because it is greater than 1 and less than 3. Right. So it is correct. So till now it is correct, 5, 3, 1, 2. Now I had put 4. 4 should be here, right? 4 should be here. So for correct, pre-order 5, 3, 1, then 2, then 4. So far clear? Then if you go right side, you can put 7 first, right? Then 8. So far okay. But now I had to put 6. Where should I put 6? I had to put here, right? Because 6 is less than 7. But now if you see the pre-order is changing, it should be actually 1. Sorry, it should be 5, 3, 1, 2, 4, 7, 6, 8, not 8, 6. So choice A is not right. Is this clear? Clear. So I will take the next tree, that is B. So I'll solve it a bit fast. So first is 5. Then I have to go left, that is 3. Then I have to go 1, that is right. Then I had to print 2, that is right side. Then I had to print 6, that is also right side. Then I had to print 4. So I cannot put 4 here because it is greater than, 4 is less than 5. So choice B is also wrong. Okay. Now let's see the choice C. Start with 5, then 3, then 2, then 4. Then I had to put 1. I had to put 1 only here, right? So at that time, this is breaking, right? So choice C is also wrong. So the correct answer should be D. Okay, you don't need to solve it. The answer should be D. But in exam, you should not solve. But here I am just solving it. So the first is 5. Then left is 3. Then left is 1. Then right 2. Then here 4. Here you have 7. Then you have 6 and 8. Okay. So this is a valid binary search tree. Is it clear to everyone? Could you solve this question? Okay. Now listen here. Everyone listen here. Okay. So it's given that we have a nested representation of a binary tree, and this is the nested representation. So it says basically X is the root, Y is the left child, and Z is the right child. Okay. So that is the representation here. So it's also mentioned that Y can be null, or Z can be null, or it can be next step. Okay, that's clear, right? So basically, if you see here, right, in this representation, you cannot have 4 values like this. Okay, you can have maximum 3 values, right? So it's already mentioned that X, Y, Z, Y can be null, Z can be null, and X is a value. So you cannot have 4 values inside the bracket. So choice A should be wrong. Similarly, you cannot have 2 values inside the bracket, so choice D should be wrong. And also, if you see the choice B, you have 2 opening braces and you have 3 closing braces. It is not possible, right? So choice B should be wrong. So the correct answer should be C. Now, actually, what is C? It's actually 1, okay, and left child is 2, 3, 4, and right child is 5, 6, 7, right? Again, if you see what is 2, 3, 4, you have 2 and 3, 4. Similarly, what is 5, 6, 7? 5, 6, 7. Okay. So this is a valid binary tree. So the answer should be C. So now listen here. So this type of problems, right? So we haven't learned this property. So mostly these properties may be wrong. I don't know. So basically, what I will do is I will try with some simple trees and try to break these properties. It is given that it's a complete binary tree. So I know it's a complete binary tree. So some examples of complete binary tree could be something like this. This is a complete binary tree. Similarly, it can be something like A, B, C. This is also a complete binary tree. I'm just seeing taking some example. I am not taking with one node, because if I have one node, then everything will be true, right? Now I'm taking this example and see what's happening here. So here the last in means whatever in order, whatever we are printing last. The in order will be BA, right? So the in order will be BA. So whatever we are printing last is actually A. Okay. And I take the post order. Post order. If I take the post order, I will be printing actually BA, right? I'm printing BA post order. That's correct. Now, if I print pre-order, 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 I will be printing A, B, right? A, B. So here the last value is B. So from this example, I know that the last in order is equal to last pre-order. This choice is wrong, right? Last in order, here I am getting A, and last pre-order I am getting B, right? So choice B is wrong. Also, I know that last pre-order is B, and last post order is A, right? Post order is A. So that means choice C is also wrong. So with this example, I am able to prove that B and C are wrong. I had to break this one, right? So if you see here this tree, what is the last in order? Last in order will be C, right? Last node in the in order will be printing B, A, and C. So last will be C. And in post order last value will be A, right? Post order last value will be A. That means last in is equal last post. This is also wrong. So the answer should be none of them. So this is the next question. Okay, now listen here. Okay, so again we have a question. We don't know exactly what is the formula for this, right? So what we know is that each node having 0 or 3 children. So that is the property we have, each node having 0 or 3 children. So I can just draw a tree something like this. Each node is having 0 or 3 children. So here it's okay. So either the node is having 0 or the node is having 3 children, right? Then what we had to find out, the number of leaf nodes, right? Number of leaf nodes. And assume n is the total number of nodes. It's not given here, but I assume n is the total number of nodes. So what is n here? In our example, it is 1, 2, 3, 4, 5, 6, 7. So n is 7. And the total number of leaf nodes, that is actually, maybe I'll call it n0, that is actually equal to 5, right? So number of leaf nodes is 5. N is equal to 7, what we are getting is 5, right? So choice A is wrong because when n equal to 7, we are not getting 7 by 2. Choice B is wrong because n minus 1 by 3 will be 6 by 3, that is 2, but we got answer as 5. Choice C is again wrong, right? Because we are getting n minus 1, 6 by 2, that is actually 3, but we are getting 5. So choice C is also wrong. So the correct answer should be D. We can even verify it with n equal to 7. It will be 2n, that is 14 plus 1, that is 15. 15 divided by 3 is actually equal to 5. Now, let's see how we can prove this. See, in exam hall, right, they don't know whether you know how to prove it or not. They need to know only whether you are answering correctly. So you can always go for some example trees and find out the solution. But I will explain you how we can do this, prove this. It may be helpful when we have a question like numerical data type questions. We may need to know how to prove all these things. Okay, so this tree has a property. So it has only two type of nodes, either with 0 degree or degree 3. Right, so let me write it as n0 and n3. So n0 means nodes with degree 0, and n3 means nodes with degree 3. Okay, so I know that total number of nodes will be number of nodes with degree 0 plus number of nodes with degree 3, right? So this will be the n. So let me call this as equation number 1. And I also know that n minus 1, that is number of edges. So 0 degree node is not going to contribute anything, but a degree 3 node is going to contribute 3 edges. So I know n minus 1 will be equal to 3 into n3, right? So that means n3 should be equal to n minus 1 by 3. N minus 1 by 3. Okay. So if you see, I want to find out the leaf nodes. Okay. Leaf nodes. That means I had to find out the value of n0 in terms of n. So in the final result, right, I don't need n3. That is the meaning. Okay, I don't need n3 because I want to express n0 in terms of n. So I can substitute the value of n3 into this equation. So I'll get n equal to n0 plus n minus 1 by 3. N0 plus n minus 1 by 3. And if you find out the value of n0, it will be 2n plus 1 divided by 3. Is this clear to everyone? I will give you 50 seconds to answer this question. That is correct. So the answer is actually C, because it is given that it is actually a binary search tree. It's a binary search tree, and we are actually doing in order traversal. So we know that if you have a binary search tree and if you are doing in order traversal, the answer should be in sorted order. So if you see, this is the sequence that is having sorted order, right? All others are not having sorted order, right? So the answer should be C. I'll give you 2 minutes for this. Okay, all of you listen here. So it's given we have a binary tree, okay, and we want to find the maximum possible height, and also it's given that the number of nodes in the left subtree is at least half and at most twice the number of nodes in the right subtree, right? So we know that to get the maximum possible height, the tree should not be balanced, right? So we have to either keep very less nodes on the left side and maximum nodes on the right side, or we have to keep maximum nodes in the left side and minimum in the right side, okay? So let's assume what we are going to do is we are going to keep less number of nodes in the left side and maximum number of nodes in the right side. Okay, this is the idea what we are going to do. Uh, so this portion will have lot of nodes. Okay, this portion will have less number of nodes. If this is the idea we are doing, so totally we have n nodes. Okay, so if you add these two, you should be getting approximately n minus 1, right? N minus 1. Okay. So the right side, let's assume you have x nodes. So here left side should be half x, right? So we are actually assuming that we should have minimum here, and it's also given at least half. It should have at least half. So if you have x here, you should have half x here, okay? Half x here. And we also know that x plus half x should be equal to n minus 1. Since actually it's asked to find out the approximate value, instead of n minus 1, I am just taking n. So I got x plus half x is equal to n, or x is equal to 2 by 3 n, right? X is equal to 2 by 3 n. So that means this portion is getting 2 by 3 n, and this portion will be having 1 by 3 n, right? So again, if you see this side, again it will get divided, right? The same process will continue. So this side will be having 4 by 9 n, right? So like that will be going. So now we have to find out the height of this tree, right? So every time actually it is getting divided. If you see this side, every time it is getting divided by 2 by 3, 2 by 3, right? So we know that if we are getting every step, if it is n is divided by 1 by 2, 1 by 4, 1 by 8, like this, then the height will be log n to the base. You just reverse this 1 by 2, you'll get 2, right? So log n to the base 2. So that we already know. So here it is actually going 2 by 3, then it will be 2 by 3 all square, like that. So the height should be log n to the base. You just reverse this 2 by 2, 2 by 3 to 3 by 2. So the height should be log n to the base 3 by 2. Actually, we have explained this in the first class itself, how to calculate the height when it is a fraction. Okay, so log n to the base 3 by 2. So this is one way of doing it. So if you think, okay, there may be a way. So assuming that left is having more than right. So in that case, again, if you see the left side, okay, here you have x, and this side you will have 2x, right? That is the maximum possible height. We want to find maximum and at most twice the number of nodes in the right subtree. That is another condition. So you can have x here and 2x here. And if you add x plus 2x, it should be n minus 1. I'm just writing n. Then again, I'm getting x is equal to 1 by 1 by 3n. So that means here x is 1 by 3n, 2x is actually 2 by 3n. So this is the same tree. See, if here I have 1 by 3n, 2 by 3n here I have 1 by 3n and 2 by 3n here. So this also having maximum height log n to the base 3 by 2. Okay, so the answer should be D. So let me move to the next slide. I have to do it very fast. Okay, 1 minute time. Okay, so now listen here. This is the binary search tree we need to construct using this sequence. So the first node will be 10. So the next one will go left, that is 1. 3 will be right side of 1. 5 will be right side of 3. 15 will be right side of 10. 12 will be left side of 15. And 16 will be like this. Okay. So what is actually height of the tree? Height of the tree is nothing but the number of edges. It is given here. See, the maximum distance of a leaf node from root. That distance is number of edges, right? So 1, 2, 3. This is the maximum distance. So the height should be 3. Okay, I will just tell what it is actually, because we haven't covered the depth first search or breadth first search. So maybe we'll see this question during the when we discuss about graph. But as we know, maybe the level order traversal, actually we will visit level by level. So first will be A, then B, then C, then D, E, F, G. This is the order actually we are visiting. So it will be equal to breadth first search actually. Breadth first search is actually you will go breadth first, right? So it will be first you'll be printing A, then you will go breadthwise, it will be printing B and C. So the answer should be breadth first search. You will see in this in detail when we discuss graphs. Okay, I will give you 20 seconds to answer this question. Okay, so I think everyone knows the answer. We had to construct a binary tree uniquely. We know that we need to have in order. So this choice is having in order plus post order. Similarly, you have in order plus pre order here. So second and third. So the answer should be B. Okay. So we have a program here. Okay, we have a program here, and the question is the value returned by do something when pointed to the root of the non-empty tree is passed as its argument, and we have 4 choices. You can actually take screenshot of this slide, then we'll move back to the previous slide. So I have a program here. Okay, so it will take some time to actually analyze this type of problems, but sometimes, right, is really easy also. So if you see, right, what we are doing here, if ptr less than left child, that means we are doing something for left child. Okay, and if it is right child, not null, we are doing something else. Okay, we are not doing the same thing for left and right. Is that clear? Because if you see here, it's left child is not null, we are doing something. Okay, and if right child is not null, then we are doing something else. So these two statements are not same. That means we are not doing the same operation for left child and right child. Is that right? Everyone agree with that? So if it is counting the number of leaf nodes in a tree, so it should have done the same thing, right? If you are counting the number of leaf nodes in a tree, so left side, how you are going to count the number of leaf nodes, you should be doing the same thing in the right side. Okay, so it is not actually counting the number of leaf nodes in the tree. If it is counting the number of nodes, again, if you see, it should have done the same thing, because how you are going to count the left subtree, it should be the same as how you are going to count the right subtree, right? So choice B is also wrong. Again, the number of internal nodes in the tree, this is also wrong, because if we are counting number of internal nodes in the tree, you should be doing the same operation in the left and right. So ideally the answer should be the height of the tree. Since we know this program previously itself, it is actually easy to analyze also. See, we are computing something, 1 plus do something. Okay, 1 plus do something. We are computing something for left child. And then actually, if you see here, 1 plus do something, PD of right child, we are doing the same thing in the right side. Right side also, we are doing the same thing, computing. Then we are finding the max. Okay, max of left side and right side. So definitely we should be computing the height. Okay, You can actually try with an example. I'm not doing it for this problem now. There are some other problems where we really need to analyze. At that time, we will see. Okay, but here we don't need to do much analysis. You can do it at home. Okay, do it at home. Okay, I'll give you 2 minutes. Okay, now listen here. Okay, it's given that it's actually a balanced binary search tree. Okay, so one thing you should understand that if it's a balanced binary search tree, then the height should be log n. Okay, so the height of the tree should be log n. I mean theta of log n, approximately log n. Okay, so the height of the tree should be log n. Then it has n leaves. Okay, n leaves. So the tree could be something like this. Okay, and finally you have n leaves. Okay, you have n leaves. So since it is height balanced and you have log and height, if you see, I'm just taking a left subtree out of this and right subtree like this. If you see, then the number of leaf nodes in the left subtree, that is here, right? It will be approximately n by 2, right? So you have total n leaves. So the left side will be approximately n by 2. It may not be exactly n by 2, but approximately it will be n by 2. And right side also it will be n by 2. Okay. Okay. So we have n by 2 nodes in the left side. Similarly, you have approximately n by 2 nodes in the right side. Now what it says is for every node, okay, each node, it's taking g of x. What is g of x? Is the minimum number of leaf nodes in the left subtree of x, comma, the number of leaf nodes in the right subtree of x. Okay, so that means time we spend for root will be minimum of these two. Here we have approximately n by 2, and here also we have approximately n by 2. So that means for this node, we are actually spending approximately n by 2 time. Is that clear to everyone? Now, if you take the node here, right, how much time we are going to spend here? Again, it will be, if you see this subtree, it will have n by 4, and this one will have n by 4. So min of this 2 will be again n by 4. So for this node, we are going to spend n by 4 time. Similarly, for this node, we are going to spend n by 4 time. So totally at this level, we will be having n by 4 plus n by 4, that is 2n by 4, that is n by 2. So the second level also, we are actually spending n by 2. Now, if you see the third level also will be n by 2, right? Here it will be n by 8, here it will be n by 8, here again n by 8, n by 8. So third level also will be n by 8. So actually every level it will be approximately n by 2. We have height log n, so it should be n by 2 into log n, that should be theta of n log. So the answer should be B. I will give you 20 seconds to answer this question. Okay, so all are getting the answer because we know that in a binary search tree, the in-order traversal is going to get a sorted order. So choice A is correct. I'll give you 2 minutes. Okay, so everyone is getting answer as C, right? This is answer everyone is getting. So we can do this. Assuming you have a k array tree, so where k is a constant, some value, and it's also given every internal node has exactly k children. That means internal nodes are all having k children. Then we have to find out number of leaves in such a tree with n internal nodes. Okay, n internal nodes. This is the question, right? So let's assume k is equal to 2. K is equal to 2, and maybe I will draw some tree with k is equal to 2. Or this is a valid tree according to this definition. Every internal node. So this is an internal node. This is an internal node, and this is an internal node. It has k, right? K is 2. So all internal nodes are having degree 2, and others are leaf. Okay. So number of leaf nodes, right? So number of leaf nodes here is 4, and 0 is 4, and number of internal nodes, that's n is equal to 3. Okay, now we can see whether these equations are correct. So we have to get number of leaf nodes. Okay, so number of leaf nodes is 4. So we should get answer 4 when we substitute n is equal to 3 and k is equal to 2. Okay, when we substitute n is equal to 3 and k is equal to 2, we should get 4. So here, if you substitute, what we'll get? N is equal to 3 and k is equal to 2, we are getting 6. So this choice is wrong. Here we are doing n minus 1, that is 2 into k plus 1, that is actually 5. Again, our answer is wrong. C is n into, that is 3 into k minus 1, that is 1, plus 1, that is actually 4. We are getting 4. And D, actually, if you see n into, that is 3 into k minus 1, that is 1. So we are getting 3, that is also wrong. So we know that answer should be C. We will prove this, okay? So it's given that we have exactly k children, right, for every internal nodes. So that means we will have only two type of nodes in this tree, that is nodes with 0 degree as well as nodes with degree k, right? These are actually internal nodes and its value is given as n, right? N internal nodes, right? So we know that nk is internal nodes. Actually, its value is given as n. So we know that total number of nodes, let's assume it's x, then it should be equal to n0 plus nk is n. So it should be n0 plus n. And we also note that number of edges x minus 1 should be equal to 0 degree is not going to contribute anything. This is having k degree, so it should contribute k edges for every node. So x minus 1 is equal to k into n, or x is equal to k into n plus 1. Right, so this is the value of x. I can substitute this value here. I will get k n plus 1 is equal to n0 plus n, right? So n0 is equal to k n plus 1 minus n, right? I can take n outside of this two values, so I'll get n into k minus 1 plus 1, okay? N into k minus 1 plus 1. So the answer should be C. I'll give you 1 minute to solve this problem. We have n vertices, okay? We don't know anything about the tree, but we have n vertices, okay? Then what should be the minimum size of x? The question is actually, even though it's asking for minimum size of x, but it says actually you should be able to accommodate any tree with that size, okay? That is the question, okay? You should be able to store any binary tree, okay? You should be able to store any binary tree with that size, okay? Remember this, okay? So the worst case we know that actually the worst case happens for a sequential representation. The worst case happens when you have a right skewed binary tree, right? When you have a right skewed binary tree. So let's assume you have A, B, C. This is a right skewed binary tree. Then what happens is actually A will be stored in index 1, and actually we will leave a space for left child. Then B will be stored in index 3. This should have been stored in 2, but it's blank. Then what will happen? We will actually keep a space for 2's left child, then 2's right child, then 3's left child, then B's right child, right? So here the index will be 7. So if you have 3, n is equal to 3, what value you are getting is 7, right? So that is nothing but actually 2 raised to 3 minus 1, right? That is 7, okay? So if you have n nodes, basically you have to allocate 2 raised to n minus 1 spaces to guarantee that you can store any type of tree. So the answer should be D. Is this clear to everyone? I'll give you 1 minute time. Okay, so everyone is getting the answer. See, it's a direct question. We know the equation also. But let's assume if you don't know the equation, what we had find out is the maximum number of nodes in the binary tree of height h. So maximum means every level should be filled. So it should be something like this, right? If this is the max height, here is actually 2, right? Height here is 2. So maximum we have actually 7 nodes. That is actually 2 raised to 3, right? Minus 1. So if the height is 2, we are getting 2 raised to 3 minus 1. Okay, so this value is height minus 1. Sorry, height plus 1. So then if you have height h, it should be 2 raised to h plus 1 minus 1. So the answer should be C. Okay, so listen here. Yeah, all are right. Its answer is A. So let me do this. So it's given we have this is in order and this is the pre-order. So we know that pre-order means this value should be the root. So A is root. And here, since A is root, I know D, B, and E, D, B, and E are left side, and A, sorry, F, C, G are right side. Okay, so even if I do post order traversal, first actually I should be printing D, B, E in some order because I haven't explored here. Then after that I should be printing F, G, F, C, G, and last value should be A. So here the last value is A. Here all the choices the last value is A, and the first three values should be D, B, E. So here it is DEF. So this choice is wrong. Here the first three values are EDB. So it is okay. Here also it is EDB. Here it is DEB. So other three choices I cannot remove. I had to go further. So if I see here the next value printed is B, that means A's left child is B. So here I have FCG. Okay. Here I have B. Now if I look into here, B's left side I have D and right side I have E. That means here I have D and here I have E. Right? So that means during the post order it should start with D, right? E, B. Right? It should start with D, E, B. So if you see, only choice A is having starting with actually D, E, B. So the correct answer should be A. I'll give you 2 minutes time. So now could you please all listen here? So here actually I cannot do with the sample because I have a big value for L and I. So basically I need to know now how to solve this problem. So that's why I told you have to also understand how to prove this type of questions. Okay. So it's given we have an n array tree and each node has n children or no children. Okay, it's given you have n children or no children. Okay, so and also so you have, maybe you can assume it is n0. That means you have no children, and you have n that is actually having n children. So only you have these two type of nodes, but it's also already given that I be the number of internal nodes. That means nn is the internal node, right? So that is given as I, and L be the number of leaves. So N0 is given as L. Okay, so L0 is given as L. Now it's they're asking for some particular value of L is equal to 41, L is equal to 41, and I is equal to 10. I is equal to 10. We had to find out the value of N, right? So we know that the total number of nodes, let me call it as X. X should be equal to N0 plus Nn, that is I plus L, I plus L, and that is equal to 41 plus 10, that is 51. So we know that total number of nodes X is equal to 51. And also we know that X minus 1, that is 51 minus 1, X minus 1 should be equal to the node with 0 is not going to, degree 0 is not going to contribute any edge. The node with the degree n is going to contribute n edges, right? So we have I into n should be equal to 50, right? 50, right? And I is already given it is 10, so it is 10 into n is equal to 50, and we know that n is equal to 50 by 10, that is equal to 5. Okay, just take the screenshot of this slide. Okay, so we have, if you see this program, we are doing something here. If you see ptr left child equal to null and ptr right child equal to null, then value is equal to 1. That means they are, see, when this will happen, ptr left child equal to null and ptr right child equal to null will happen only uh, if the node is a leaf node, right? Only the node is a leaf node. So the answer should be something related to leaf node. So if you go here, the choice is C. Actually, most probably this may be the correct answer. So let's see. Okay. So let's assume you are having a tree, something like A, B, C, and you are passing the root. Okay, that is A. Now what happens? You are coming here and checking ptr not equal to null. That is true because you are calling this program with a as the root. Okay, so you are checking ptr is not equal to null, then ptr left child not equal to null, ptr right child, this is not, this condition is not satisfied, will come here. So the value here is 0, right? Value is 0, that is initialized here. Value is equal to value plus, so value is equal to value plus, we are calling get value of ptr right child plus get value of ptr right child. So we are calling left child plus right child, right? So we'll be calling two recursive calls, one with b and one with c, and then we will be returning these values, right? We will be adding these values and we will be returning. Now we come to b. If you see b, what happens? Left child is null and right child is null, so value is 1. So here we will be returning 1. Similarly, this call C, if you see left child is null, right child is null, so this is also going to return 1. So 1 plus 1 is 2. So this, if you give this tree, this program is going to return the value 2. Now, if you see this choice, number of nodes in the tree, that is wrong. If that is the answer, we should have got 3. And the number of leaf nodes in the tree, that is 2, and we are also getting 2 here. Number of internal nodes, we have internal nodes here 1, but we got answers 2. That means choice B is wrong. Height of the tree, height of the tree here is actually, height of the tree is 1, but we got 2. Okay, so when you are taking an example, you have to make sure that you already know the answer should be somewhat this one. So all other choice you should be able to break fast. So that's why I took a tree. That's I could actually make all the choices false very fast. Okay, I will give you 20 seconds time for this. Okay, so the answer is actually B. We have discussed this already. We had to construct a binary search tree, right? And it's actually post order traversal is given. So we know that we using a stack, we can just do in one pass, we can construct a binary search tree. So the order should be theta of n. Okay. Okay. Now listen here. Okay. So let me make it clear. What we had to find is what is the number of nodes in the tree that have exactly one child. Okay, so this is the question. So I'm just drawing one tree. So if you see the number of nodes in the tree having exactly one child, that is, if you see this node is having 2 child, this is having 0, this is having 2, this is having 0. Only this node is having exactly one child. So if for this tree, the answer should be 1. And maybe I will draw another tree, maybe like this. And here this node is having exactly one child, this node is having exactly one child, this node is having exactly one child. So the number of nodes in the tree that have exactly one child here is 3. Okay, but we have one more condition, that is every node has an odd number of descendants and every node is considered to be its own descendant. So this is the one more condition we have satisfied. Okay, so this is the condition we have satisfied in this tree. So you know what is descendant, right? This is A, this is B, this is C, this is D, this is E, and this is F. So if you see, normal definition of descendant is B, C, D, E, F. All are actually descendant of A, right? So here actually it says we should consider that particular node also its own descendant. So the descendant of A actually is A, B, C, D, E, F. Okay. If you see, this is 6, but it says that we have to have an odd number of descendants, right? So this is not a valid tree for our example because every node is not satisfying this condition. Okay, if this is A, this is B, this is C, and this is D. So number of descendants of A is actually A, B, C, D. That's again an even number. So this is also not a valid tree for our example. So we have to find a tree first. Along, any doubt?
Sir, 4 plus 1 5 വരില്ലേ അവിടെ odd number വന്നില്ലേ because that node itself act as a descendant എന്നല്ലേ?
Which one? This one?
Yes.
The second problem?
Yes.
Yeah, this node is acting as a descendant. So this is actually having three descendants. See, 1, 2, 3, three descendants plus a, that is actually 4, right?
Yes, correct, sir. Yes, yes.
Right? We want odd number, right?
Yes. Correct.
Okay.
എനിക്ക്
Okay. So that means this is also not a valid tree. So somehow we have to create a tree that actually having odd number of descendants, including that node. Okay. So let me start trying a tree. Okay. So let me start with some node A. Then what happens actually? I need to have odd number of descendants including A, right? So if I exclude A, that means I need to have even number of descendants, right? Even number of descendants if I exclude A, right? Even number of descendants, right? Even number of descendants. If I exclude A. So that is a condition, right? Including A, actually you are getting odd number of descendants. That means if I exclude A, I need to get even number of descendants, right? Okay. Okay, so let's assume you have only in the left branch some nodes here. Okay, some nodes here. You don't have a right branch. Okay, and every node should satisfy this, right? So this node also, let's assume you don't have a right branch. Okay, so let's assume you don't have a right branch. So that means this node also should satisfy that whatever here should be even, right? This node also should satisfy that whatever here should be even. So this even plus this odd, plus this one will become odd, right? Odd, right? And plus a will become again even, right? So basically you want even here. That means you need to have both branch. You cannot just go with one branch. Okay, so that is one thing you should understand. You cannot just go with one branch. Always you should go with you need to go with two branch to get a even number of descendants. Is that clear to everyone? Okay. So now that means you have to start with A, then you have to have left child and right child, because if you don't have left child, what I'm saying again, I will say once again, if you don't have right child, let's assume you have only left child, then what happens is, so I will have some nodes here. This should be even, right? This should be even because for every node, right, you should have even number of descendants excluding itself. So this should be even, right? So this even plus this one is going to become odd, right? So my condition is excluding A, the number of descendants should be even. That is actually going to break here because I haven't took right. So I have to take left as well as right from A. I hope it is clear to everyone now. I had to take actually left and right with A, right? Again, if I have a branch here, I have to take left and right. See, I cannot actually move only with left. So here also the condition, if I just, I'm not thinking about this portion. So if I just think about this tree, I have to satisfy the condition. Every node should satisfy the condition. So that means if I am going down, I have to go in both ways. Here also, if I am going down, I have to go with both ways. So that means you cannot actually go in one direction. You have to always go in both directions. Okay, so if you actually move in both direction, that means your number of your degree basically will be either 2 or it will be 0, right? If you are moving in both direction, your degree should be either 2 or you are not at all moving, then your degree should be 0. Is that correct? So that means you will not have any node that is having degree 1. See, you are moving in both direction, that means degree is 2, or you are not moving, that means degree is 0. So that means you will not have any node with degree 1. If you don't have any node with degree 1, then exactly one child condition will be 0. Because you don't have any node with degree 1, that means the number of nodes in the tree that have exactly one child will be equal to 0. Maybe I will show you the next slide. You take a screenshot of this slide. Okay, come back to here. I will give you 2 minutes. Okay. Now listen here. Actually, we can solve this very fast, but before that, let me just tell you how these expressions are actually evaluated. We have told this during the expression tree. Anyway, the idea of solving an expression is actually do a post order traversal. So if you do post order traversal of this tree, what happens? So you first process this node, right? That is the post order. You print 7. Then you will come to here. Then you will print 3. Then you will come to 4. Then you print 4. Then 3. Then 2. Then this operation. Okay. Once you see an operation, what we'll do, we'll apply this, right? Apply that operation. So that means you are doing 7, 3, 4. Then 3. This is the operation you are doing. Okay. Now you'll come here and you'll print this one, right? This one. So you need two arguments, that is 4 and this one. So you'll say 7, 3, 4, then this one. Okay. Then 3, 2. So this is the order. Then you will come to this node. Then you will print this node, value again. So that means you need two arguments. So this is one argument and this is another argument. So it will be 7. Then you have 3. Then you have this operation. Then the remaining, right? 4, up arrow, 3, down arrow. Okay. Now finally you will see this down arrow operation. So you have 7 here, 7, then down arrow, then 3, then up arrow, then 4, then up arrow, then 3, then down arrow, then 2. Okay. So this is the way actually you will be solving this expression. Okay. I'm just telling you this. You know already this idea, right? Everyone knows this. Okay. Okay. So now let's see this expression. This is the expression also given that this is having highest precedence, and it's also given this is right associative, and down arrow is left associative. Okay. So how this expression should be processed according to this condition? Let me write it again. So you have 3, 4, 3, down arrow 2. Okay. So we know that up arrow is having high precedence. That means that operation should be done first. And also, if you see, we have two up arrows continuously here, right? And it is given that it is right associative. That means you have to do first this one, then this one. Okay. So that is the way we will be completing, right? Then you can do down arrow, and it is left associative. That means you will be doing this first, then this. Okay. So this is the way actually we should process this. Okay. Now if you see, we have a 4 up arrow 3 operation needs to be done. So here if you see, there is no 4 up arrow 3. Here if you see, we have a 4 up arrow 3. Okay. And if you see this choice, we don't have a 4 up arrow 3 node. Similarly here also you don't have. So the answer should be, will give you 60 seconds. Okay, now listen here. Okay, so it is given that you have a balanced binary search tree. Okay, so I already told you, if you have a balanced binary search tree, then the height will be log n. Okay, the height will be log n. If you have n nodes, right, height will be log n if you have n nodes, and the searching time will be the height of the tree, that will be log n. Okay, so if you have n nodes, the time complexity will be theta of log n, right? The time complexity will be theta of log n. Now instead of n, you have n into 2 raised to n, right? So instead of n, you have to pass n into 2 raised to n, right? So you have theta of log n into 2 raised to n, right? Now what is log a into b? Log a into b is log a plus log b, right? So it is equal to theta of log n plus log 2 raised to n, right? Log 2 raised to n is actually this portion is log n, and this portion is log 2 raised to n should be n into log 2. Log 2 is 1. So you get theta of n plus log n. We know that log n is low order term, so we can write it as theta of n. So the answer should be C. Next question. So could you take the screenshot of this portion? Okay. So the answer is A. That is true. This is the answer. So let's see. We can take an example. If you see here, right, n dot left is null, then we are doing something, else we are doing something. Okay, so we want to know what is B2 and that what is B1. So to reach B, this portion directly, I had to make left is equal to null, right? So I can take an example, something like this, and see. I need to return actually the height, right? Height should be 1. Okay, so here the value should be 1. So let's see how what will happen if I pass this tree here. So if I pass this tree here, what will happen? N is equal to null. No, n is not equal to null because I am calling with a, right? So I am calling with a. N dot left is null. No, n dot left. Yeah, n dot. Okay, sorry, I should have taken a tree like this. Okay, I should have taken a tree like this. Okay. So now n dot left is null. No, n dot left is not null. So I will come to else portion. Okay. So what it is doing? H1 is equal to height of n dot left. So again we are calling. Okay. So remember we have to return get the answers 1. Again we are calling with p. Okay. So h1 will be equal to height of n dot left. Okay. So we are calling with b. And what b we are coming here, n dot left is null. Yes, left is null. N dot right is null. Yes, b dot right is null. Then we are returning 0. Okay, so we are returning 0. So 0 will be returned. So that means h1 will be 0, right? h1 will be 0. Right? Now if n dot right is null, okay. So n dot right is null. Yes, it is null. So what happens is actually we are just returning 1 plus h1, right? So that means we have to go here. Okay, so I have to take a tree that is a little bit bigger, I think. So let me take b. Okay, so this portion is, sorry, this is c. Okay, this is c, and this portion returns 0. Now I am checking. So h1 is 0. If n dot right is null, n dot right is not null. So I am calling h2 is equal to. Okay, so h2 is equal to, I am calling height of n dot right. So I am calling with actually c. Okay. Now c left and right is null. So this is also going to return 0. Now h1 is 0. Now h1 is 0 and h2 is 0. I know the height of this tree is 1. h1 is 0, h2 is 0. Right? So what, now I am here, right? So what it should return actually? So that is what we had to find out. B2 should be 1 plus max of h1 comma h2. Okay, because both are returning 0, I had to get 1. So it should be 1 plus max of h1 comma h2. Right? So the answer should be 1 plus max of h1 comma h2 for B. So here it is correct, here it is correct, here it is wrong, here it is wrong. So the answer should be either A or it should be B. So far clear? Okay, now let's just take another tree. Maybe I'll take a tree with one more node. Maybe I'll put a D here. And I know now if I pass A, then it will call B, then it will return 0. Okay, so I know h1 is equal to 0, right? h1 is equal to 0. Then I will be calling with C. Okay, I will be calling with C. So C has a left child that is not null, right? N dot left is equal to null. Then we will go here. Okay, so maybe I should not put here. I should put here. Okay. So n dot left is equal to null. I am reaching here. Okay. Then n dot right equal to null. No, n dot right is also not equal to null. So then we are returning B1. Okay. So what we should return here? That is the question, right? So we should return actually the height of this tree plus this node, right? Height of this right tree plus the C should be returned here, right? So height of this, so 1 plus, it should be 1 plus height of the right tree. Okay, so we should be returning 1 plus height of this right subtree. Okay, so the answer should be actually A. We'll give you 5 seconds time. Just if you say binary search tree, then it is doesn't mean that it's balanced. Okay, binary search tree can have a height of order of n. The answer should be C. I'll give you 1 minute. Okay, so the answer is actually D. So let me solve this. So it's given that this is the pre-order sequence, right? So I know that pre-order, the first node will be root. So this should be 30. Okay, so all the nodes here should be the left side should be less than 30 and right side should be greater than 30, right? So next node is 20. That means it should be less than 30. So 20 should be here, right? And the next node is 10, so it should be less than 20, should be here. The next node is 15, so it should be greater than 10, should be here. The next node is 25, so it should be here. Then you have 23, that should be left side of this. You have 39, that should be right of 30. Then you have 35, that should be left of 39. You have 42, that should be right of. So this is the binary search tree. Now you know how to do post order traversal, right? The post order traversal should be starting with 15. So this choice is wrong. Then the next value should be 10. So this choice is wrong. The next value should be 23. So this choice is wrong. So the answer should be D. Give it 2 minutes. Listen here, okay? So it's given we have a binary tree represented using pointers. And the question is the best upper bound on the time required determine number of subtrees having exactly 4 nodes. So for example, if your node is or tree is something like this, subtrees having exactly 4 nodes, right? So if you see this subtree is having exactly 4 nodes. Similarly, if you see this subtree, you are having exactly 4 nodes. Maybe I'll delete this. Okay, so this subtree is also having exactly 4 nodes. So we have to find all subtrees, or we have to find the number of subtrees having exactly 4 nodes. Okay, so the idea is very simple actually. You can recursively find it. You actually, for example, from here, you find the number of nodes in the left subtree plus number of nodes in the right subtree plus 1 will be the size of this tree. For computing that, you have to compute again from here. You have to compute number of left subtree plus number of right subtree plus 1. So if you compute every node, right, number of left subtree plus number of right subtree plus 1, then in that recursion loop, right, you know, whenever you are getting 4, that means you are having actually a subtree of size 4. So I can actually write an algorithm. I will write it fast. For example, I have result, that's assume it's a global variable and it is initially 0. This will give us the number of subtrees having exactly 4 nodes. Okay, now I have a recursive algorithm count t. This is going to count the number of nodes for each node. So if t is null, then return 0 because you don't have any node. Now I am actually going to use a variable node count. This will be local to that recursive definition. So it will be local to every node. Node count is actually equal to 1 plus. So initially node count is 0. So node count is equal to 1 plus count of left child plus count of right child. Okay, so this is a recursive definition. I'm just counting 1 plus left child count plus right child count. Then I will check if node count is equal to 4, then result is equal to result plus 1. Okay, so this is the simple algorithm. I am just finally I can just return result. Okay, everything is finished, then I can just return the result. Is this clear? So basically, I'm just counting the number of nodes in the left subtree plus right subtree, and I'm just checking if the value is 4, then just increment the result. Okay. So this algorithm, you know, right? Actually, this is basically you are visiting every node 3 times. It's actually like all the 3 algorithms are mostly like that, right? So this is actually going to take order of n time. Now it's given that order of n is equal to order of n raised to a into log raised to bn means log n all raised to b. right? Log n all raised to p. So that means a should be the value should be equal to order of n. That means a should be equal to 1 and b should be equal to 0, right? A should be equal to 1 and b should be equal to 0. Then so that this term will get vanished and you will have order of n, right? So a should be equal to 1 and b should be equal to 0. And if you substitute that here, you will get the value as 1. Okay. So the answer should be 1. So let me see the next problem. I will give you 1 minute time. So basically I want to get the maximum value, right? The maximum value. So whatever here, okay, this tree, okay, whatever its evaluates, plus I am evaluating this value, right? So I need, that means the maximum value means this portion should be maximum as well as this portion should be maximum, right? Now what we are doing here, we are doing, if you see here, we are doing a minus operation, right? So that means I need the maximum value here. That means this portion I need to have maximum value, and this portion I need to have minimum value because I am doing minus. So this is the idea. This is applicable to everyone, everywhere. So I let me maximize this. To maximize this, I can choose 0 or 1, but I will choose 1 both sides because then I will get 1 plus 1 is 2. So this value is 2, right? Here I want minimum, right? Because I am going to subtract something from 2. So I want minimum. So I will take 0 from this side and 1 from this side. So 0 minus 1 will be minus 1. So 0 minus 1 will be minus 1. Now 2 minus minus 1 will be 3. So 2 minus minus 1 will be 3. So I got 3 in the left side. Now similarly here also I need the, here I have plus. So that means I need maximum here and maximum here. So I have minus here. That means I need maximum here and minimum here, right? So I can take 1 in the left side, 1 in the left side, and 0 in the right side. So 1 minus 0 will be 1, right? Here I am adding, so I can have maximum both sides. So I can take 1 here, 1 here, 1 plus 1 is 2. Now I am adding this 1 plus 2, that is 3. So I have 3 plus 3, answer is 6. I will give you 10 seconds. In order traversal, that means second time, right? So first we'll go to P, then go to Q, then go to S, then come back to S. So you have to print S. Then you'll be coming back to Q, then you'll be printing Q. Okay. Then you are coming back to P, so you'll be printing P. Okay. So every thing you see, everything starts with SQP. Now you will go to R, that is first time. Then you are going to T, right? Again, we'll come back to T. So SQPT. Everything is SQPT, okay. Then you will come back to R, that is second time, so SQPT R. So this choice is wrong, this choice is wrong, so it may be SQPTR, SQPTR, okay. Then you will go to U, then you will go to W, then you will come back to W, that is second time, so you will print W. So the answer is A. Next problem. So the question is, actually we are getting a balanced binary search tree. So you know the height should be log n. So something like this, okay. The height should be log n, and you have some nodes, something like this, okay. So the height should be log n, okay. Now it's given that we are given two numbers L and H, and wish to sum up all the numbers in T that lie between L and H. Okay. So let's assume you are given L and H. You have to add everything between L and H, right? So let's assume you search for L and it is here. Okay. So let's assume you search for L and it is here. And so searching for L will take log n time, right? Because the height is log n. So searching for L is going to take log n. Now similarly, you can search for H. So let's assume it is here. H is here. Okay, H is this point. So searching for that also will take log n. So I know now this is one point and this is another point. So basically, I have to add all these points. Okay, all these points. Okay, because this value will also, all the values here should be less than or equal to H, right? So I have to basically add all these values. That's all, right? So I know the lower bound, I can get it with log n. I can get the upper bound with log n. I had to add all these things. How much time it is going to take add all these things? It depends on how many nodes are there. So we have, it is given that we have m such nodes, okay, m such nodes. So you can add all these things in m time. So it will be log n plus m. So it should be log n plus m. Okay, so this is the time complexity of this algorithm. So we know that log n plus m should be equal to big O of n raised to, this is log n plus m, should be equal to n raised to a log n all raised to b plus m raised to c log n all raised to d. Okay, this is what it is given. So we know that a should be equal to 0 because we don't have an n term here. N raised 0 will be 1. So a is 0. B should be 1, right? Because log n. We need log n, right? So B should be 1. M raised to C. C should be 1. C should be 1. And D should be equal to 0, right? Log n all raised to D. Log n all raised to 0. We should get out of this log n term. So we got A equal to 0, B equal to 1, C equal to 1, and D equal to 0. So if I substitute this value, A is 0, B is 1, that means 10. C is 1, that is 100. D is 0. So I get 110. Okay, so the answer is 110. Okay, let's solve this. 5 seconds time. So 3, 5, 7, 8, 15, 90, 25. This is valid, right? 5, 8, 9, 12, 10. It's not valid. 2, 7, 10, 8, 10, 8. This is not valid. 4, 6, 7, 9, 18, 20, 25. This is valid. So 1 and 4 are true. Okay. What are the complexities of insertion and deletion of a key in a binary search tree? Okay. See, whether we are doing insertion or we are doing deletion, what we will do first thing is actually we will try to search for that element. Okay. So insertion, we will try to search for that element, and finally we'll actually end up in a blank place and where we are inserting. Similarly, deletion also, we have to first search for that element to delete it. So that search is going to take order of n if it is not a balanced binary search tree. Okay, so the answer should be order of n for both insertion and deletion. See, we have to find the maximum as well as minimum number of nodes in a binary tree of 5, right? Minimum is very simple. So this will be the minimum number of nodes of height 5, right? 1, 2, 3, 4, 5. Okay, so this is height 5. This is the minimum number of nodes in height 5. That will be 6, right? So the answer should be either A or D. Okay. Now we have to find the maximum. So we had to fill all the nodes something like this. Now if you see here, the height is 2, or we can even go one more level if you want. So the height here is 3. How many nodes we have? It is actually 2 raised to 4 minus 1, right? So if the height is 3, the answer is 2 raised to 4 minus 1. So if the height is 5, it should be 2 raised to 6 minus 1. 2 raised to 6 is 64. 64 minus 1 is 63. So answer should be 63 and 6, right? 63 and 6. So the answer is A. Yes, that is correct. We have 20 leaves. That means we will have 19 nodes with the degree 2, right? I'm not going to prove it again. We have proved this several times. Give you 1 minute. 1 minute time to solve this. So it's a straightforward question. Everybody is getting answer 67. So if you construct the tree, it will be 71. Left side is 65. Right side will be 84. Then here you will have 69. Then 67. Then 83. Right. So this will be the answer. Okay. Yeah. This is again straightforward question. It is 199. Right. Okay, so let's see what is the maximum height with 50 nodes. Maximum height, right? So if you have 3 nodes, for example, if you have 3 nodes, then you can draw like this. The maximum height will be 2. So if you have 15 nodes, the maximum height should be 40. Choice A should be wrong and choice D should be wrong. Maximum height is 40. Now, minimum height, right? So if you have 15 nodes, so we know that we can draw like this. That is exactly 15 nodes. If you count, it will be exactly 15 nodes, right? 8 plus 4 plus 2 plus 1, it is 15. And the height is 3, right? So this is the minimum height, and this is the maximum height. So 3 and 14 will be the answer. It's given you have a post-order traversal as well as in-order traversal, right? So you know that post-order traversal, last one will be the root, so 1. And if you see, the right side is 3 and left side is remaining things. So right side is 3 and left side you will have all the nodes, right? So if again you come to the post-order, you can leave this 3 because we have only 1 in the right side. Then 2 is the root. If you see, right side is 5, right side is 5, and remaining elements are on the left side, right? Now if you can leave this 5 and take the 4, 4 will be here. And if you see the right side, you can see 7 only, right side you have 7 only. So you can leave this 7, and then you're seeing 6, so the left side is 6. Now if you come here 6, you have only 9 in the right side, so this is 9, and only now you have only 8, that is here. So here the height is 1, 2, 3, 4. So the height of the tree is 4. Okay, so let me explain this again once again. So you have an expression here. So you have hash and dollar. So if you see here, okay, actually, first this is what is getting computed, right? So that means a dollar has higher precedence than hash, right? So dollar has higher precedence than hash. Also, you see we have dollar here and dollar here, but we are actually computing B and C first. That means dollar has higher precedence and dollar is actually left associate. Okay, so dollar has higher precedence and dollar is left associative. This statement is correct. Okay, this is wrong. This statement is correct. See, this statement is correct, and this choice D is also wrong. So answer may be either A or C. So it's talking about hash. So if you see here, we have 2 hash, and if you see this figure, first we are computing I hash F. That means it is computing this first. That means it is right associative. Okay, so hash is right associative. So pre-order traversal of binary search tree is given, and which of one of the following is the post-order traversal of the tree? I will give you 20 seconds. So it's given the pre-order traversal is this one, right? So that means the root is 15. So the root is 15. So what we know is in post-order traversal, the last node will be 15, right? The last node will be 15. So that means choice A is wrong and choice C is wrong. Okay, so last node will be 15. Choice D. So you have 50. You are starting from 15. Okay. Uh, then what happens actually? Let me think about this. Okay. So you are actually printing here 10, right? So what it means actually? Uh, this side,
Right.
right, should be having 10, right? That is the meaning, right? Is that right?
Yes.
Right? So
Yes.
this side you should have value 10, right? But that is not possible, right? Because you have 15 here. This side you will not have 10. So that means the answer should be B. Okay. This is one of just looking into it and doing it. You can actually construct the using the pre-order. You can actually construct the binary search tree very fast, and then also you can do the post-order traversal. That's also possible. Okay. It's given let T be a full binary tree with 8 leaves. Okay, listen, everyone listen here. Okay, it's given T be a full binary tree with 8 leaves. So that means you should have a tree something like this, right? Because you have 8 leaves. Okay, and let me call these leaves as A, B, C, D, E, F, G, H. Okay. Now what we are saying is suppose two leaves A and B of T are chosen uniformly, that is without any bias, and independently at random. Okay, what is independently means here? So you're going to choose two nodes. Okay, so you're just randomly going to choose one node. So let me call it as A. That is the first draw. Okay, now in the second row, is it possible to have A again? The second time, if I am taking, I am choosing two leaves randomly, right? In the second time, is it possible to again select A? If it is not possible to select A, that means first the second row is actually depending on the first, right? See, if you are first you are choosing A, and second time you have to take two leaves, and second time if you are not allowed to take A again, that means the first time you choose A, that is why I am actually not allowed to take second time, right? So that means that two draw are not independent because there is a dependency. First time you choose A, that is why you are not allowed to take second time A. It is given that it is independent. That means the two times you are taking, both times it should be independent. That means even if you take A in the first time, second time also you can take A. That is the meaning. Okay. So if you assume that you are actually drawing balls, it is something like you are drawing a ball, then actually you are replacing it. Again, you can draw. Okay. So that is the meaning here. It is independent. Okay. Clear? It's mean that you can actually take A, that is possible. Also, it means that first row you take A, then B, then A. This is also valid. Okay, so these are not same, these are actually different. Okay, that is the meaning. Okay, so how many different pairs you can actually take? Two pairs, right? How many different pairs are possible? How many different pairs are possible? Since you have 1, 2, 3, 4, 5, 6, 7, 8, so you can take any of these 8 in the first row. Again, you can take any of this in the second row. So you have 8 into 8, that's you can actually have 64 pairs. Okay, so these are the maximum possible pairs. 8 actually 64. Okay, 64 pairs are possible. Okay, now so that we know 64 pairs are possible. Now they are saying something about the distance between A and B. Okay, so what is the distance between A and B? The distance between A and B is the number of edges in the unique path between A and B. Okay, number of edges between the unique path between A and B. So the distance between A and B. So is it possible to have a distance of 0? Distance of 0. Yes, it is possible. You can have a distance of 0 when you are taking AA or BB or CC or DD or EE or FF or GG or HH. Right? In all this case, you can have a distance of 0 because there is no need of any edge from moving from A to A. Right? So you have 8 such combinations. 8 such combinations are having distance 0. What about distance 1? Distance 1. Distance 1 means you are randomly taking two nodes, and the number of edges between that path, or if you take a path between that two nodes, the number of edges should be equal to 1. So is there any pair where the distance is 1? Can you find out any pair where the distance is 1? No, there is no pair with the distance is 1. So actually, if you observe, you can see the distance should be actually even. So the distance with the 1 is not there. Distance with 2, it is there, right? Distance with 2, if you take A and B, you can see the distance is 1, 2, right? 2, right? Similarly, you can take C and D, or you can take EF, or you can take GH, or the reverse, right? You can take BA, DC, FE, or HE. Okay, so that means with the distance 2, you have 8 pairs. 8 pairs. Okay, 8 pairs with the distance 2. Now, what about distance 4? How many pairs are possible with the distance 4? 1, 2, 3, 4. That is also fine, right? So you have AC, then you have AD, right? Similarly, you can have BC, BD, right? Then you have EG, EH, FG, FH, and you can just reverse this. So here you have 8, and then reverse you will have 8, so you will have total 60. Okay, so with distance 4 you have 16 pairs. Okay, distance 4 you have 16 pairs. Then what about with the distance 8? how many pairs will be there? Distance 8, how many pairs will be there? Sorry, distance 8 will not be there. Distance 6, right? AE is an example with the distance 6, right? So you can have AE, AF, AG, AH, and then you can have BE, BF, BG, BH. You can have CE, CF, CG, CH. Then you can have DE, DF, DG, and DH. Right? And so this is actually 16, and you can also have the other pair. So for example, EA, EB, like that, right? So this is actually 32. So 32 pairs. Okay. So we know totally we have 64 pairs, and if you randomly take a pair, it can have distance either 0, or it can have either distance 2, or it can have either distance 4 or 6. Now the question is, we had to find out the expected value of the distance between A and B. Okay, so we had to find out the expected value of distance between A and B, and we know that we have only possibility 0, 2, 4, 6. Okay, so let us assume you have a random variable R is equal to actually representing these distinct values. So you can have random variable to hold 0, 2, 4, 6. Okay, so this random variable is nothing but it represents the distance between the two leaves, right? 0, 2, 4, 6. Now what is expectation of R? That is what we have to compute, right? Expectation of R will be equal to probability, sorry, expectation of R will be equal to 0 into probability of R equal to 0 plus 2 into probability of R is equal to 2 plus 4 into probability of R is equal to 4 plus 6 into probability of R is equal to 6. So this will be the expectation. So 0 into something you don't need to calculate. So 2 into probability of R is equal to 2. So we have 8 pairs out of 64, right? So probability will be 8 by 64 plus 4 into probability of R is equal to 4. So probability of R is equal to 4, we have 16 pairs out of 64. So that will be equal to 4 into 16 by 64 plus 6 into probability of R equal to 6. R is equal to 6, you have 32 pairs out of 64, right? So 32 divided by 64. So this will be the expectation value. So if you compute this, this will be equal to, I think it will be equal to 4.25. Okay.